should be of interest to anyone who needs to collect data. How much data is necessary? It's a number of procedures in Statgraphics that are designed to answer those questions for you. I don't talk about them very often, which is why I decided that today it would be useful to examine some procedures in Statgraphics that are designed to help you figure out how much data you need. Now, to get started, I thought I would talk about data requirements in general. Obviously, one of the most important questions that statisticians get asked very frequently is, how much data do I need? And of course, when people ask us that fairly simple question, they expect a simple answer. Unfortunately, the answer is almost never simple. And like a good psychiatrist, I think statisticians are most likely to answer your question with another question. Because there's no simple rule, well, like always take 30 observations. It really depends upon what questions you're trying to answer, and more importantly, how well you need to know the answer. Because data will be data, and we won't always be right when we compute statistics with respect to what we're trying to estimate. But we can at least be sure that the probability of making correct decisions and correct estimates is large. Now, in general, it's certainly true that the more data you collect, the better. At least from a statistical perspective, it's true. You get better estimates, you get more powerful tests, the larger the sample size. On the other hand, from a practical point of view, more data costs more money and takes longer to collect. So from a practical point of view, you'd like to keep the sample size small, while from a statistical point of view, you'd like to keep the sample size large. And it's obviously a balancing act between those two requirements. Another point to keep in mind is that the information that we gain from each additional data value that we collect goes down as the sample size increases. There's a decreasing return as the sample size gets large. If you look at the standard errors of most statistics, they go down as 1 over the square root of n. So typically, 4 times as much data only gives me twice as much information. We need to keep that in mind as we think about the sample sizes. And the last point I would make in general before we start looking at particular examples is that all data are not created equal. You can collect a lot of data, but if it's the wrong data, if it's badly conditioned, there may be little you can do with it. Whereas if you collect the right data, as we try to do in things like when we design experiments, then often we can get a lot of information out of relatively small samples. Okay, now, if we look at the sample size problem, Statgraphics actually has something like 7 different procedures that are built into the menus to help you determine what a reasonable sample size is for different types of problems. And we're going to be actually looking at these 7 problems this morning. The first problem has to do with estimating or testing a single population parameter, where I'm going to go out and I'm going to take a sample of items and try to estimate a mean or a standard deviation or a proportion or a rate, something like that. The second problem is comparing estimates from 2 or more samples. You know, I may have 2 methods for producing something. I take a sample of some items from one method and some items from another and want to test whether or not there's a significant difference between those 2 methods. We have a procedure in Statgraphics for comparing capability indices, for estimating capability indices. There's one for constructing control charts, another for developing statistical tolerance limits. We have a procedure that will help tell us how big an experiment we need to do if we're doing screening. And there are also a couple of procedures in Statgraphics for developing acceptance sampling plans. Now, as I said, I'm going to be showing you an example of each of these procedures as we go through here today, hoping that by showing you examples, you'll be able to see what might be applicable for what you need to do. Now, when we talk about determining sample size, there are two basic methods. The first method, which I'm going to call the margin of error method, is based on estimating a parameter. You know, if I'm going to go in, for example, estimate a mean, estimate a proportion, estimate a standard deviation, something like that. And with method number one, what we do is we try to find the sample size, little n, such that the margin of error for the estimate is acceptably small. The margin of error is basically the plus and minus that we would have in a confidence interval that we do for the estimate. And for example, I might want to go in and estimate the mean to within plus and minus 10% and ask how much data do I need such that the confidence interval for the mean is no bigger than plus and minus 10%. We're going to call that the margin of error method. And it's going to be method number one. Method number two has to do with doing statistical tests. What we do with method number two is we typically set up a set of hypotheses, a null hypothesis and an alternative hypothesis. And we ask, what sample size do we need so that the power of the test is sufficiently large? Where power has to do with the likelihood or probability that the test will give me a statistically significant result when some alternative hypothesis is true. Okay, and as we go through and look at the different examples, sometimes I'll be using the margin of error method, sometimes I'll be using the power method with respect to determining what the most reasonable sample sizes are. Okay, now let's start with my first example, which will have to do with estimating the parameter of a single population. And the example here is going to involve the margin of error method. And I decided, since we're in the midst of a presidential election here in the United States, to talk about the following problem. Suppose we want to estimate the proportion of voters in the United States who would select Mitt Romney, who's one of the Republican candidates for president at the moment, over Barack Obama if there were a head-to-head election for the president today. Okay? Pollsters love to go out and ask a sample of people, who would you vote for if the election were held today? The one way of determining how many voters to ask, what sort of sample size we would need, would be to pick the margin of error that we were willing to tolerate. For example, you can imagine going out and asking some number of voters, who are you going to vote for, Mitt Romney or Barack Obama? And as a result of that poll, you'll come back and say, well, you know, 53% said they would vote for Mitt Romney or something like that. I have no idea what it is, but I'm just making up a number. What we try to do in such a case is be sure that we ask enough voters, take a large enough poll, so that the margin of error associated with that estimate, when I come back and say 53%, is no more than, let's say, 3 or 4 percentage points. And I've written it down here as a confidence interval, as a requirement that we estimate that proportion to no worse than plus and minus 0.03. Now, in the United States, when we report polls, when polls are reported, they almost always tell us what the margin of error is. And the margin of error is the plus and minus, actually, in a 95% confidence interval for the numbers that are being reported in the poll. Now, to do that in Statgraphics, what we need to do, and I'll pull up Statgraphics now for a moment, is go to the main menu to Tools. And you will see under Tools there is a section on sample size determination. 6 of the different examples that we'll be talking about today are on this particular menu, the sample size tools determination menu. The last one, the acceptance sampling one, is actually under SPC. But all the others are on the menu under tools sample size determination. Now the problem we're interested in this case in is the one sample problem. We're going to take a single sample from a single population and estimate a parameter. Now the procedure here gives us a choice. It asks us, do we want to estimate the mean? Do we want to estimate the standard deviation? Do we want to estimate a binomial proportion? Or do we want to estimate a Poisson rate? In the case of determining, deciding between Mitt Romney and Barack Obama, that's going to be a binomial problem. Binomial 2 names. People are going to tell us, well, I'm going to vote for Romney or I'm going to vote for Obama. So I'll pick the proportion. I also will need to tell the program down in the field here that says hypothesize proportion what I expect the proportion to be, at least approximately. Because it turns out that the variability in a statistic that estimates a proportion depends upon what the actual proportion is. If you happen to look at the equations, and I'm not going to spend a lot of time on equations today. The worst case scenario, actually, the case when you need the biggest sample size in estimating the proportion, is when the proportion is around 0.5. And actually, in most U.S. presidential elections, it's around 0.5. Might be as low as 0.4 or as high as 0.6, but actually the sample size doesn't differ very much. If, on the other hand, you're trying to estimate a proportion down around 1%, then you can get away with smaller samples. But I'll put in here an expected value of 0.5 and press OK. Now, when I press OK, a second dialog box will come up. And here is where I tell the program whether I want to use that margin of error method or the power method. In fact, there are 4 choices typically when I look at the sample size procedures in Statgraphics. I can tell it that I have a requirement with respect to the absolute error, that I want to estimate the parameter, whatever it is, to plus and minus something. And here I'm going to actually type my 0.03, which will tell the program to find me a sample size that will allow me to estimate the percentage of the voters that will vote for a particular candidate to within plus and minus 0.03. On the other hand, I could have asked to estimate it to within a relative error. That choice would allow me to say to within, let's say, plus or minus 10%, 10% of whatever the true value is. And then we have choices for the power approach, which I'll talk about in a few minutes. And then there's also a choice in most of the procedures, sample size, where you can tell it what the sample size will be, what you can afford, for example, and it'll tell you what the errors in the power actually are. But as far as sample size determination is concerned, if you want the program to determine the sample size, then we'll either take the margin of error approach or we'll take the power approach. So I'll tell it anyway, for my first example, that I want to estimate the proportion to within plus and minus 0.03. Okay, down here there's a field for confidence level where I tell it what level of confidence I want to use for that estimate, and the most common is 95%, so I'm going to leave it there. There's also a field for alternative hypothesis. Here I can choose either not equal, less than, or greater than. Now, this applies when I'm doing the power approach, as we'll do in the next examples, where I actually set up a set of hypotheses. It also, though, affects whether the sample size here will be based upon a two-sided confidence interval or a one-sided confidence bound. We'll see, for example, when we go and estimate CPK, a capability index, that we're not particularly interested in how large the CPK is. We just want to be sure that it's not too small. In this case, though, I'll just leave it at not equal, which will give me a two-sided confidence interval. Let's press OK, at which point a analysis window will pop up, and hopefully you can see this. It says that the required sample size is n equals 1,098 observations. I need to ask 1,098 people, are you going to vote for Mitt Romney or are you going to vote for Barack Obama? And if I do, I'll be able to estimate the proportion to within plus and minus 0.03, assuming it's somewhere around 0.5. Now, if it turns out to be less than 0.5, the confidence interval will be even tighter than plus and minus 0.03. But if it is around 0.5, if I ask 1,098 people, who are you going to vote for, I'll be able to estimate the proportion to within plus and minus 0.03. Okay, now this is the relevant statistic, the binomial proportion, for a lot of interesting problems. In this case, we're talking about choosing between two candidates for president. There are also a lot of problems when I go in and take a sample of items from a production lot, for example, and classify them as either defective or not defective, good or bad. That's a similar sort of problem, a binomial problem, and the same sort of approach applies in that particular case. Okay, so that's the simplest approach. Let me get back to my PowerPoint here, where we go in and we ask how many samples do I need to estimate a population parameter or a single parameter to within a given margin of error. And incidentally, we have posted for you to download later on these slides. So quickly, hopefully you can download the slide afterwards and take a look at them again. But the answer in this case turned out to be 1,098 voters that we need to poll in order to estimate their preferences to within plus and minus what would be 3 percentage points. Okay. Now, that's a margin of error approach. Let's look at a second example, a little bit different example. This is going to be an example of comparing two means. I'm going to suppose, to make it interesting, that I have two processes. A new process that I'm working on, which I think is much better than an old process. But I've got the old process as well, which we've used, let's say, for many years. I intend to go out and take a sample of N1 measurements from the new process and N2 measurements from the old process, hoping, of course, to be able to prove that the new process is better than the old. We wish to be 90% certain that we'll get a statistically significant result if the mean of the new process is at least 20% greater than the mean of the old process. Okay, now, if there's not much difference between the new and the old, I probably won't have a good chance of being able to demonstrate it. So I have to pick a number, and I've picked arbitrarily 20%. And I'm going to say if my new mean is 20% bigger than my old mean, I want to be 90% certain I'll get a statistically significant result. Now, in order to approach this problem, what we do is we set up a set of hypotheses, a null hypothesis and an alternative hypothesis. In this case, the null hypothesis, which I'll have to believe unless I can prove otherwise, is that the mean of my new process is no better than the mean of my old process. The alternative that I hope to prove, and that's typically the way these hypotheses are set up, the alternative hypothesis is what you're trying to demonstrate. The alternative hypothesis is going to be that the mean of my new process is greater than the mean of my old process. And what we want to do is we want to make sure that we take enough samples so that the probability of rejecting the null hypothesis in favor of the alternative is at least 0.9 if the new process, the mean of the new process is 20% greater than the mean of the old process. Okay? That's the standard power method, where you set up a set of hypotheses, a null hypothesis and an alternative, and you ask, how much data do I need such that if a particular alternative is true, I'll be able to demonstrate it with a given level of confidence. Okay? Now, the place to answer that sort of problem in Statgraphics, let's go back to Statgraphics for a moment. Let's close off what I was just doing. Okay, get back to an empty data sheet. Okay, the place I'll want to go to do that will be to the Tools menu to sample size 2 or more samples. Okay. This is where I can go if I want to compare, for example, 2 means, or 2 standard deviations, or 2 binomial proportions, or 2 Poisson rates. We also have an option for comparing several normal means. That would be what's typically done in a one-way analysis of variance, where you have data from several different groups, several methods, and you want to demonstrate that there's a significant difference among 3 or more methods. Okay, now let's see how we would solve our problem here. First off, we need to pick what we want to compare, which in this case is 2 normal means. Secondly, we need to specify the hypothesized difference, and that refers to the null hypothesis. What does the null hypothesis say? Well, the null hypothesis with respect to the difference of the means is that there is no difference. And so I'm going to leave the value 0 there, which would result, if we were doing a statistical test, in a t-test of the hypothesis that the means were the same. It also wants me to tell it approximately what I think the means are going to be. In this case, I'm going to put in the value 30. Where'd that come from? Well, it came from what I know about this particular process. Turns out that that number actually doesn't affect the sample size. It might in some other cases, but when you're comparing 2 normal means, actually what the means are is irrelevant. What's critical when you're comparing means is the field over here, where it says hypothesized within group signals. The program wants to know if I go out and take a sample of items from the new process, let's say 30 samples or whatever I need from that new process, what's the standard deviation going to be amongst the items from the new sample? Now, what we're going to do is the standard t-test that actually assumes that the standard deviation in the new process will be the same as the standard deviation amongst items if I took them from the old process. Actually, the t-test is fairly robust against that assumption, works fairly well whether or not that's true. But I need to put in a number for the standard deviation. Now, you say, but I haven't done my experiment yet. I'm just sitting here trying to decide what the sample size should be. So actually, it is a little bit of a chicken and the egg problem. In order to tell you how much data you need, I need to know how much variability there's going to be in your data. I mean, if your samples don't vary much, you don't need many samples. But if your data is all over the place, you need a lot more samples. Now, that means often that you need to go back and look at some historical data, or you need to go out and take a preliminary sample, and then we'll tell you how much you really need. One way or another, though, it's quite critical that we know what the standard deviation is amongst items within a group. And I'm going to put in the value 5 as something that might be reasonable. Again, this has to be done on a very specific case-by-case basis. But let's just put in the value 5 so we can go in and get an answer. Now, let's press OK. And again, what this will do is it'll bring up a second dialog box. Looks very similar to what we saw before in the case of estimating a single population parameter. In this case, though, rather than specifying the absolute error, I'm going to go down and click where it says power. Now, if you take the power approach, what you do is you specify the probability that you'll be able to reject the null hypothesis in favor of the alternative when the alternative is true. And the way I formulated this problem is I said I wanted to be 90% certain, you will remember, that I'll be able to get a statistically significant result if the mean of the new process is 20% bigger than the mean of the old. Well, on the previous screen, I specified that the means were around 30. 20% of 30 is 6, if I can do my math correctly. So I'm going to put here where it says difference to detect 6. So I'm basically saying get me enough data such that if there is a 20% difference in the means, which would be 6, 36 compared to 30, that I'll be 90% chance, they'll have a 90% chance of detecting that. That's called the power of the test. At the same time, I have to go down here to the confidence level field and specify what would be called the alpha risk. The alpha risk is the probability that I will reject the null hypothesis when it's true. Now, most of us are 95% people. We do 95% confidence intervals. We run with an alpha risk of 5%, which means we don't call things statistically significant until our p-values get below 0.05. At least that's the default in Statgraphics unless you change it. And I'm going to leave it at the default, which basically says that I won't reject the null if the null is true. I won't say there's a difference if there's not more than 5% of the time. On the other hand, if there is a difference and it's as big as 6, I want to reject the null 90% of the time. Now, I also need to come down here where it says alternative hypothesis and tell it what sort of test I want to do. In this case, the alternative is what we call a one-sided alternative. I'm trying to demonstrate that my new process, its mean is greater than the old process. That's called a one-sided test of hypotheses. I'm not just trying to show a difference between old and new. I'm actually trying to show that the new is better, larger than the old. So I'm going to set that to greater than. One last field over here, it says sigma, to be estimated or known. Now, most of the time when we do a t-test, we estimate what the standard deviation is from the data, and that is the default. The reason we have a known button here is basically so you can replicate some of the examples in a lot of textbooks. A lot of textbooks, rather than relying on students' t-distribution, make things simple for you and assume that you know the standard deviation. That's the within group standard deviation for which I entered a 5 on the previous screen. So that, and in order for people to be able to replicate the textbooks, there's a little radio button there for known. And if you click on known, it'll use a z-score instead of a t. But in the practical world, most of the time, we're going to be estimating the standard deviation. So I'll just leave that as to be estimated and press OK. And now we'll pop up a screen, and it will tell me, and again, I hope you can see this, it says the required sample size is 13 observations from sample 1 and 13 observations from sample 2. And again, to be sure it's done what it was supposed to, you might want to read the stat advisor. This procedure determines the sample size required when comparing the means of two normal distributions. Assuming that the standard deviations of the normal distributions equal 5, 13 observations are required in sample 1 and 13 to have 90% chance of rejecting the hypothesis that mu1 minus mu2 is 0 when the true mu1 minus mu2 is 6 using a one-sided test. Okay, I usually like to read the stat advisor to be sure, in fact, that I entered everything the way I intended to. Anyway, it says 13 observations should be taken from each of the samples. By the way, it will also plot for you when you do one of these analyses the power curve. The power curve shows you the power of the test versus various alternatives. Power is the probability that I reject the null hypothesis in favor of the alternative. Or in this case, the probability that I'll get a statistically significant result and be able to say that the new process is better than the old. What I had asked, it's actually a curve. The probability of getting a significant result depends upon what the actual difference is between the new process and the old process. I basically specified in doing the setup here 2 points on this power curve. I asked initially that there be no more than a 5% chance of rejecting the null if there was no difference. That's the alpha risk. And then I also asked that there be a 90% chance of rejecting the null if the difference was in fact 20%. So what I've done is I've actually, in setting up this problem, pinned down 2 points of that power curve. 5% at 0, 90% at 6, and then it figured out that, okay, to do that, you'll need 13 observations from each of the samples. Okay? So that's a very classic sample size type of a problem, taking the power approach. Okay. And again, if you take a look at the PowerPoint slides, you can download them, as I said, from our website. You can see step by step what I've just done for you. Okay, well, let's go to a third topic. Let's talk about capability indices. Statgraphics, as you might know, is widely used for determining the quality of products and services that are being produced. One method for quantifying the quality of a product is to compute something called a capability index. A capability index measures how capable the process is. And by that we mean how capable is it of keeping the vast majority of what I'm making within certain specification limits. Probably the most popular capability index is something called CPK. CPK is defined as basically the distance from the mean, mu, to the nearer specification limit. Now, sometimes you only have a lower spec or an upper spec. At other times, you have both a lower and an upper. But basically, CPK is the distance from the mean to the nearer specification limit divided by 3 sigma, 3 times the standard deviation of the process. And typically, people refer to a process as being capable if CPK is at least 1.33. That's the most common rule. There are other rules. Some companies like it to be 1.5. Some are happy if it's 1. I'm going to take the most common requirement, and that is that it be 1.33. The question I want to ask is, how many samples should I take from my process so that I can get a reasonable estimate of CPK? Now, unfortunately, a lot of people take estimates of CPK from samples that are much too small. CPK, it turns out, is a very difficult statistic to estimate. You can probably tell by the way it's defined. It has a mean at the top and a standard deviation, mean in the numerator, standard deviation in the denominator. Okay? Standard deviations in particular are difficult to estimate. So what I'd like to look at here is what is a reasonable sample size in order to estimate a capability index. Now to do that, I'm going to go back to Statgraphics, and let's close out what we've been doing. I'll just say File New again to get back to an empty data sheet. Okay. There we go. And now I'm going to go to Tools, Sample Size Determination, Capability Indices. Now, the way this runs is the first thing you will see is this dialog box here. Statgraphics can figure out what a good sample size is for estimating 3 popular indices: CP, CPK, and CPM. Definitely the most popular of those is CPK, so I think I'll just leave that where it is. The way we're going to do this is we're going to use the margin of error method. We're going to go back to the first of the 2 methods that I demonstrated, general methods for determining sample sizes, and basically specify the margin of error. The first thing it's going to ask you is, what do you think CPK is going to be approximately? And I'll say, well, I hope it's going to be around 1.33. Then I can tell it, okay, if it is around 1.33, I want to be sure, actually, whatever it really is, that I can estimate it within plus and minus 10% with 95% confidence. In other words, I want to be 95% sure that the true CPK of my process is within 10% of what I estimate it to be. Now, 10% is sort of big. I mean, that's the difference between what? That's between a capability index on the low side of 1.2 or on the high side of 1.46. So it's almost an interval of 1.2 to 1.5. Okay, that's a fairly large error. But unfortunately, people, you might not even like this answer. If I ask for a relative error of 5%, my answer is going to be even worse. So let's leave it at 10% as a reasonable number. If I press OK, the program will estimate for me how many samples I need to estimate the capability index to within plus and minus 10%. And it basically says I need 154 observations to be within 10% of the true CPK. And it actually creates a plot for you here, and it will tell you that, for example, that if you come up with an estimate of 1.33, and let me bring up my locator functions, that if you get, for example, an estimate of 1.33, there's basically 1.3, move this up, there we go, there's about 1.33. If you get an estimate of 1.33, you can be 95% certain that the real capability is no less than about 1.2. Okay. The blue bound here is a horizontal line. That would be your estimate. The lower red bound is a 95% lower bound. So the statement you'll be able to make if you get a capability index of 1.33, a CPK of 1.33, is that you're 95% certain that the capability index, the true CPK, is at least 1.2. Now this does bother people. People actually like to take capability indices, CPKs, and compute them from 30 observations. Believe me, a CPK from 30 observations has a huge margin of error. At 154 samples, it has a margin of error of 10%. So you can just imagine what the margin of error might be if you take only 30 samples. I'm not sure what it is, but it's pretty large. Actually, I guess I could probably figure out what it was. If I go back to analysis options here, let me say, okay, give me a 20% error. What sort of sample size do I need? About 39. Okay, I sometimes do this trial and error method. Okay, how about a 22% error? 33. How about a 25% error? 26. So it's not quite that bad. It's probably about 23%. Yeah, there we go. If you take a CPK and compute it from only 30 observations, you may be off by 23% from the true CPK. And in fact, it looks like if I got a 1.33, the true CPK could be as low as 1. Okay, 30 observations is really not enough, I hate to tell you, to get a decent estimate of CPK. Okay, so there's a place you can go to figure out what a reasonable sample size is. How if you're doing a control chart? There's in Statgraphics that'll tell you what sort of samples you need, what sort of sample sizes should you take for your control chart. Now I'm going to consider in particular control charts that are based on group data. Typical example would be someone that makes batches of items or batches of a product. And from every batch takes K samples. From those K samples, it's common to construct what are called X bar and R charts. From every batch, I go in and take K samples, and I take the average of those K samples and plot them on an X bar chart, and the range of the K samples and plot them on an R chart. Question: how many samples should I take from each batch? What should K be so that my control chart has reasonable power? And again, what we're going to do here is take the power approach, because whether you think of it this way or not, a control chart is basically doing a hypothesis test. The null hypothesis, typically, I'm in control. The alternative hypothesis, I'm out of control. And every time you plot a point on a control chart and determine whether or not it's outside the control limits, you're doing a test of hypotheses. Okay, so it's natural to approach the control chart problem from the power method. Now, I'm going to formulate it in the following way. I'm going to first set down the null hypothesis. The null hypothesis is going to be the process mean is equal to my target value. Think about yourself running a process, monitoring it in real time. If you're doing what you're supposed to be doing, you've got the mean set at some target value and you're just humming along. Okay, that'll be the null hypothesis. The alternative hypothesis will be that the process mean is equal to the target value plus some delta. That it's actually shifted from its target value either up or down by an amount equal to this value delta. Now, the way we approach the control chart sample size problem is typically through what's called the average run length. The average run length, or ARL, will be the average number of batches that I'll have to inspect and put on my control chart before I get an out-of-control signal, if in fact the mean shifts from its target value to this alternative value. So for example, I might go in and I might say, okay, give me enough samples from each batch such that if the mean shifts by an amount delta, I'll get an out-of-control signal on average, let's say, within at least 3 batches, no more than 3 batches. So it's typically set up the sample size, if you're doing a control chart, through the average run length. Now, where Statgraphics does this, I bet you'll guess where it does it. It does it under Tools, Sample Size Determination, Control Charts. Now, the first dialog box that will come up for this sort of a problem will ask us, what kind of chart are we going to create? Are we going to be creating an X-bar chart, a moving average chart, an EWMA chart, a Q-sum chart, and 2 different kinds of Q-sum charts? Or perhaps we're plotting attribute data, maybe a P chart or a U chart. Okay? My example here is probably the most common, and that is an X-bar chart. I go in, I take K samples from each batch, compute the mean of those K samples, and plot it on an X-bar chart. Now, there's a number of things we need to tell the program in order for it to tell us how many samples we should take from each batch. The first thing we need to do is specify down here where it says process parameters what the target mean is, and I'm going to put in 30 as my target mean, and what the process sigma is, and I'm going to again put in 5. Now, this will probably come from some previous data collection someplace. Process mean, but that might in fact be your target. I hope that I'm operating at a mean of 30. The process standard deviation, 5, though, that's the normal natural variation in the process when it's under control. So I need to put in a mean, I need to put in a standard deviation. I can tell it that I'm doing a 2-sided control chart or a 1-sided control chart. Usually if it's an X-bar chart and I'm trying to keep the mean close to its target, I have both upper and lower control limits. Down here where it says design requirements, I now need to tell it something about the alternative. And I'm going to ask it now to control the average run length for a target mean. I probably should not have called it target here, for an alternative mean of 35. The actual null hypothesis is 30. The alternative hypothesis is 35. So that's a delta of 5. Or because the process sigma here is 5, that's a 1 sigma shift in the process mean. And I'm going to tell it that I want to detect a 1 sigma shift in the target mean on average within 3 batches. So there's a section here where it says desired ARL, desired average run length. So I'm saying, tell me how many samples I need to take from each batch so that if the mean shifts by 1 standard deviation, I get a signal on average within 3 points on that control chart of 3 batches. If I press OK, it'll give me an option for things to plot, and then we'll go ahead and figure out for me how many samples I need to take. And it says over here, hopefully you can see it, that the required sample size is 7. You should take K equals 7 observations from each batch. The average run length at the target will be 2.76. Now, because of the discrete nature of the sample size, I can't get an average run length of exactly 3. So it looks for the smallest subgroup size that will give you an average run length less than or equal to what you ask. And in this case, if I take 7 observations from each group, I will get an average run length of 2.76 at that target of 35. It also tells me that the in-control average run length is 370. If my process mean doesn't shift, it stays right at 30 where it's supposed to be, I will get an average run length of 370. Now, that's standard for any 3 sigma control chart. On average, you get a false alarm every 370 observations. And in fact, over here, I plotted what's called the ARL curve. It peaks at the null hypothesis of 30 at the false alarm rate, which is about 370. 1 false alarm every 370 observations. What I asked for, though, was an average run length of 3 if the mean shifted to 35. So it turns out that if that's my requirement, I should take 7 samples from each batch. Okay. All right, as I said, what I'm trying to show you here this time is a number of different examples, different things that Statgraphics can do. I know all of you don't do control charts, but I bet some of you do. Okay, let's move on to example number 5. Example number 5 has to do with statistical tolerance limits. Statistical tolerance limits are becoming more and more popular, it seems, particularly with people who have specifications and are trying to show that their process is capable of meeting the specifications. What a statistical tolerance limit does is it bounds a specified proportion of a population with a specified level of confidence. For example, take a look at my middle paragraph here. Typical example. Suppose I wish to demonstrate that I am 95% confident that at least 99% of measurements obtained from items I am producing fall within my specification limits. Okay? It's called a 95-99 statistical tolerance limit. Okay? I'll do this by going out and taking a sample of n items from my population, constructing the tolerance limits, and if the entire tolerance interval is within the spec, then I have demonstrated compliance with the spec. Now, the way Statgraphics approaches this, you can see in my last paragraph, is by finding a sufficiently large sample such that the expected width of the tolerance interval is some fraction of the distance between the specs. For example, I can say, tell me how many samples I need to take so that the expected width of my tolerance interval is no more than, let's say, 50% of the distance between the specs. And you'll need to go out and take so many, whatever it is, observations. Now, the place we do this in Statgraphics, let me, again, close off what I've been doing here. I always like to go back to an empty data sheet, even though it takes a moment to clear everything out. Okay, there we go. To do this, I'm going to go to Tools, Sample Size Determination, Statistical Tolerance Limits. Now, Statgraphics will compute statistical tolerance limits on the assumption, on various assumptions, either that your data come from a normal distribution, that they come from a log normal distribution, or that they come from a Weibull distribution. We even have an approach where you don't have to make any assumption about the distribution. It's a non-parametric approach. But typically, that's going to require a lot larger sample than if you can reasonably assume that one of the other three distributions is reasonable. So I'm going to leave it at the default right here, which is normal, and tell it that I believe my samples come from a normal distribution. Now, if it's a normal distribution, I need to tell it what the mean and standard deviation are. I'm going to specify, in this case, a mean of 50, a process mean of 50, and let's say a standard deviation of sigma of 5. Now, I can either do two-sided tolerance limits, as I would do if I had both an upper and a lower spec, or I can do one-sided tolerance bounds. One-sided tolerance bounds, for example, lower limit only, would be done if you only had a lower spec. Or if you only had an upper spec, you could ask for a upper tolerance bound. Okay. I'm going to assume I have check down here. I'm going to put the specification limits. I'm going to let my lower be 20, my upper spec, and I'm going to ask for a interval, a 95-99 tolerance interval. That's an interval which will tell me with 95% confidence where 99% of my population falls. Okay. Now, down here where it says allowance, what you do is you specify the relative width of that tolerance interval. And I'm going to tell it right here that I want to take enough samples so that my tolerance limits are no wider than 50% of that spec. I noticed I was having power problems with the computer laptop I'm using here, so pardon me for just a moment while I make sure that it's recharging. Okay. Anyway, my specification is 20 to 80. I want tolerance limits that are no wider than 50% of that distance. If I press OK, the program will figure out how many samples I need to take. And, oh, here it is. I didn't see it for a second. The required sample size is 76. I need to take 76 of my population. If I do, then I'll get this sort of a tolerance interval over here. Here you see the tolerance limits. They run from about 35 to 65, which is about 50% of the distance between the spec. Remember, the spec went 20 to 80. If I take 76 observations, I'll expect my tolerance limits to go between about 35 and 65. That's the expected location. The reason I put in an allowance, incidentally, is because when I actually collect the data, my mean will be off a little bit, my standard deviation will be off a little bit, so the actual tolerance interval I get will be shifted right or left, maybe a little wider or a little narrower. By putting in an allowance of 50%, I've given myself a fairly good margin of error again, so that if I'm doing what I'm doing, I've got a very good chance that my tolerance limits will be completely within the spec. Anyway, if I take 76 observations from my population, my tolerance limits will be no wider than 50% of the spec. Okay, I thought that might be an interesting example. What else do I have? Well, let me go back to PowerPoint for a moment. That was example number 5. You can construct statistical tolerance limits, and it will tell you how many samples to take, such that your tolerance limits are no wider than some fraction of the distance between your spec. Okay, let's go on to example number 6. Example number 6 has to do with constructing a screening design. Now, a screening design is a statistically designed experiment. in which you vary lots of factors. I go out into my process and I start changing the temperature, changing the concentration, changing flow rates and pressures and a bunch of things, with the goal of identifying which factors have the biggest impact on my process, or in particular on one or more response variables that I'm interested in. Okay, if you've done any design of experiments, almost surely they started with screening designs. These are things like two-level factorials, fractional factorials, Plackett-Berman designs, and so forth. In fact, I put on the slide here, most screening designs contain experiments at 2 levels of each of the factors. Typically, you'll pick a low level and a high level, because low and high, 2 levels, that's enough to show you whether a factor makes a difference. So I pick a low temperature and a high temperature, low concentration, high concentration, and I do experiments at the lows and the highs. Frequently, additional experiments will also be put in at some central value of all the factors. They're called center points. You take a middle temperature, a middle concentration, a middle flow rate, and do some runs where everybody's set at some medium level. That does 2 things. It lets you get a clean estimate of the experimental error, the repeatability of the experiment. It also lets you get a sense of whether there's any curvature present. Since your factors are typically only being run at 2 levels, you sort of have to assume things are linear. If you try some experiments in the center, you can get a sense of whether things really are planar, or whether maybe you need to go to a more complicated 3-level type experiment. Okay? Now, the place to determine sample sizes for experiments is again under the Tools menu. Just minimize that window. It's under Tools, Sample Size Determination, Screening Designs. Now, what this will do is it will pop up a dialog box showing you all the different types of screening designs that Statgraphics knows how to construct. And if you go to the design of experiments, you can add section, you could ask it to construct any of these types of designs. The designs include full 2-level factorials. They include fractional factorials of resolutions 5, 4, and 3. They include irregular fractions, mixed-level fractions, Plackett-Berman designs, and so forth. Now, I decided in the PowerPoint slides I've prepared to ask it to generate the best designs for all the designs that are either resolution 5 or resolution 4. Resolution 5 designs, incidentally, are designs that can estimate all of the main effects of the factors and also all of the 2-factor interactions. Okay? Tell you whether certain factors interact with others. Resolution 4 designs, on the other hand, estimate all the main effects fine, but they start confounding the 2-factor interactions. They can give you a sense of whether there are interactions present, but they can't necessarily tell you which factors interact with which others. Resolution 3 designs, well, they start confounding the main effects with the 2-factor interactions, so I think I'm going to stay away from those. I also will tell it how many factors I intend to experiment with, and I'm going to put in, just as an illustration, 5. Now, what it's going to do, it's going to figure out for me the best design of each of these various types. Okay, so it's going to say if you want to run a full factorial, you need to do so many runs. If you want to do a resolution 5 fractional factorial, you need to do this many runs. If you want to do a Plackett-Berman design, you need to do this many runs. Okay, now, the way we're going to do this is as follows. First, there's some other fields. I can tell it maximum runs per block. If I was worried about some lurking variable, maybe day-to-day variability, and I can only do 8 experiments per day. I might put in a value 8 here, telling it, and by the way, give me block designs that have no more than 8 runs in a given block. When we set up a designed experiment, we can tell it things like that, and it will block the runs optimally into certain sizes. I'm not going to bother with that here. I can tell it that I want a minimum number of center points. So for example, if I wanted at least 3 center points, regardless of what else it decided to do, I could put in 3. I'm not going to worry about that either. I also need to tell it, and this is fairly critical, the experimental error sigma. As in almost all the other cases, I need to tell it what the standard deviation is. And in this case, it's the standard deviation of the experimental error, which you might also call the repeatability of the experiment. Suppose I took a certain set of factor levels. Set temperature at something, concentration at something, flow rate at something, and so forth, and did several experiments at those same combination of the factors. What's the standard deviation going to be in the response? Okay. Now again, this might require doing some preliminary experiments or looking at some earlier data to get an idea of what the standard deviation actually is. Now, I'm just going to leave it at 1 for now, because you'll see in just a moment I'm going to do things in a sort of relative manner. So I'll just leave it at 1. Remember that. I'm telling it the experimental error is 1. Okay. The second dialog box that comes up is that similar dialog box we've seen before, where we can tell it to control the absolute error or the relative error or the power. Now, when I'm setting up the experiments, I typically like to do it through power. And the way power works in this case, you specify the desired power. That's the chance of getting a statistically significant result. And I'm telling it I want a 90% chance that I'll get a significant result. Okay. At a particular effect to detect. And here you see something where it says effect to detect. Now, if you remember the 2-sample problem I did in comparing 2 means, I was comparing the mean of the old process with the mean of a new process, and I had to tell it what delta I was looking for. Here, I'm going to tell it what effect I want to be able to detect. In effect, in the screening design, is defined as the difference between what happens at the low level of a factor and what happens at the high level of a factor. Okay, what happens at low temperature compared to high temperature? What happens at low concentration compared to high concentration? The effect is actually the difference between the mean at the high level of temperature, for example, and the mean response at the low level of temperature. Now, I've typed in the number 2 here, telling it that I want to be 90% certain that I can detect an effect of magnitude 2 or greater. That's the smallest effect I want to be certain I can see. Now, if you remember that the experimental error, the sigma, I left it at 1, this says I want to be 90% certain that I can detect an effect equal to twice the experimental error. Well, the experimental error, that's the sigma of the noise. So anything less than 2 sigma is pretty incidental in comparison to the noise. So 2 seemed to me to be a reasonable value. And again, as always, I specify the confidence level. That's the p-value that I use to determine if an effect is statistically significant. All right, let's press OK. If I press OK, the program's going to go in and figure out for me different screening designs that will give me that sort of power. It's actually looked at various types of designs, the factorial designs, the half fractions, irregular fractions. Those are fractions, irregular fractions, incidentally, where the number of runs is not a power of 2. Mixed level fractions. A mixed level fraction actually has 3 levels of one factor, 2 levels of all the others. And it says I can get the power that I'm looking for by running a 32-run full factorial, or, for example, a 22-run resolution 5 fractional factorial. And here it has determined that if I run a half fraction of a 2 to the 5th, that's basically a fractional factorial design with 16 runs, and add 6 more points at the center. I hope you can see there's a column here that says center points. So if I run this particular design here, 16 corner points and 6 center points, I have about a 91.5% chance of seeing an effect of magnitude 2. Now again, it can't get exactly 90%. So what it does is it puts enough runs in until it gets at least 90% power. And now you can choose amongst these. You can see some of the designs have 22 runs, some of them have 24 runs. Believe me though, this half fraction is nice. It's got resolution 5. Some of the others are only resolution 4 or even approximately resolution 4. It consists of 16 corner points and 6 center points. It also makes a plot, incidentally, of these different designs. Okay, I'll move this around a little bit so you can see the labels. It also plots out for me the power curves for each of the designs. Now you may remember my specification was that if the effect was 2, I wanted 90% power. So I specified basically this point up here on the power curve, and it found the best designs of all those different types, minimum number of run designs. When I say best, I mean designs with the smallest number of total runs that would give me the power that I wanted. So I would think that in this case that would be a pretty good design, a half fraction. Do the 16 runs, add 6 center points, and you'll be able to get the sort of power that you need. All right. One more example. That was my screening design example. One more example, then I'll take some questions. Example number 7, acceptance sampling. This is the one procedure that's actually in Statgraphics, not under the tools menu. It's actually under the SPC manual. And it basically has to do, is most widely used at least, when you're doing incoming inspection. Suppose, for example, a shipment arrives at your warehouse consisting of a lot of sample of lot size, let's say capital N. You're going to take a subsample of that lot, let's say little n items, from the capital N items. Based on the sample, you're going to decide either to accept or reject the lot. Classic acceptance sampling problem. You're not going to look at every item. You're going to take a sample of little n and decide to reject capital N based upon the sample. Okay, now the obvious question is, how many samples do I have to take from that lot? Now, Statgraphics will handle 2 different situations. We can do acceptance sampling by attribute or acceptance sampling by variable. In the case of attribute sampling, you basically take little n items, inspect each item, and classify it as either good or bad. Then there's an acceptance number that's determined called C. And if the number of bad items out of little n is less than or equal to the C, you accept the lot. So you may take 100 items that have an acceptance number of 5. So you look at 100 items. If the number of bad ones is 5 or less, you accept the lot. If it's more than 5, you reject it. Okay, that's an attribute sampling plan. A variable sampling plan is a little different. Again, you take little n items from the lot of capital N items. But this time, instead of inspecting each item and classifying it either as good or bad, you measure some characteristic of each item. You then take the mean and standard deviation of the n measurements, little n measurements. And if the mean is far enough from the nearest specification limit, you accept the lot. If the mean gets too close to your specification limits, you reject the lot. That would be a variables plan. Now, to do these in Statgraphics, as I said, we needed to go to SPC. Before I do that, I'm going to close this off, though, and get myself back to a clean Statfolio. Now I'm going to go to SPC, and you'll see there is a separate menu item under SPC for acceptance sampling. And I'm going to start with a standard attribute plan. Okay, now it's going to open up a dialog box for you. And actually, in order to explain this dialog box, I have one more PowerPoint slide that I should have showed you. Here it is. In setting up an acceptance sampling plan, what we're going to do is we're going to define 2 hypotheses and use the power approach. I told you again, we have the margin of error method and the power method. This is going to be the power method. I'm going to set up 2 hypotheses. The null hypothesis will be the lot is good. The alternative hypothesis, the lot is bad. Now, I need to be a little bit more specific than that. And specifically, what I do is I pick 2 percentages for the defective items. I'll call the good percentage the AQL, the acceptable quality limit. For example, I might say I will consider the lot to be good if I have no more than 1%, let's say, defective items. 1% would be called the acceptable quality limit. Okay? To define a bad lot, I create something called the LTPD, the lot tolerance percent defective. For example, 3% might be my alternative. I'm basically saying, anything less than 1% is really good. Anything greater than 3% is really bad. I then define the producer's risk, which is alpha, and the consumer's risk, which is beta. The producer's risk will be the probability of rejecting a good lot, right? Here I've sent you a good lot and you rejecting it. I don't want to do that very often, maybe 5% of the time, because I can't always be right, but let's say no more than 5% of the time. The consumer, of course, is worried about something else. The producer is worried about the chance that some sampling plan will reject a good lot. The consumer, on the other hand, worries about the probability of accepting a bad lot. That's typically called beta. Okay? So what I have to do, typically, if I set up an acceptance sampling plan, is I define the AQL, the LTPD, and then alpha and beta. And that's exactly what the dialog box back here in Statgraphics is going to ask me to do. Well, first off, it's going to ask me what type of plan I want to create. There are a number of other types of plans. The one I'm most comfortable with, the one I'm going to demonstrate for you here, is called an OC plan, an operating characteristic plan. It's the one in which we basically control the producer's risk and the consumer's risk. I also need to tell it what the lot size is. Now, until now, we've assumed if we were taking samples from a lot, that the lot was basically infinite. Lot size was not an input. Here it is. And in fact, I'm going to tell it as an example. Let's suppose I'm going to take a sample of 10,000 items. No, pretty big lot, 10,000 items. Okay. Up here, I will define the acceptable quality level, which I'm going to put in as 1%. That's the good level. The lot tolerance percent defective, I'm going to put in as 3%. That's bad. And now I'm going to put in the consumer's risk and the producer's risk, and I'll put in both in at 5%. What we are going to ask the program to do is find an acceptance sampling plan so that there's only 5% chance of rejecting a lot if it has only 1% defective items, but at the same time only a 5% chance of accepting a lot if it has 3% defective items. Basically, I'm controlling 2 points on my power curve, and it's going to come up with an acceptance sampling plan for me. So let's press OK, and let it do a little work. There we go. It says, here it is, generated sampling plan. You should take a sample of 473 items from the lot of 10,000. Inspect them. You can accept the lot if 8 or less of those 473 are defective. Any more than 8, you reject the lot. Over here, you'll see that, well, it's, in this case, actually, it's not the power curve. It's the inverse of the power curve. Power is typically the probability of rejecting the null hypothesis. In these plans, we typically plot 1 minus power, which is actually the beta risk. And it's called the operating characteristic curve. In this sense, we will interpret what I'm plotting here as the probability of accepting a lot. And remember, what I said is I wanted only 5% chance of accepting the lot if it had 1% defective items, and a 95% chance of accepting if it was 1% defective, 5% chance of accepting if it was 3%. Okay, the power curve is just 1 minus this. But this, it's better usually in the acceptance sampling case to plot the OC curve, the probability of accepting a lot. Now, if it comes in at 2% defective, somewhere between the AQL and the LTPD, well, it's going to be what it is. In this case, there'll be about a 40% chance of accepting the lot if it's 2% defective. But you see, the way you work, the way the whole thing works is you pick a number for what's really good and a number for what's really bad, control the risk of making the wrong decision at those 2 points, and base the sample size on that. So it says I need to take 473 items, inspect those, and if 8 or less are defective, I can accept the lot. Now, that's acceptance sampling by attributes, assuming that I'm not measuring anything, I'm just inspecting it. If we can measure something and base our conclusions about whether to accept or reject the lot on a measurement, we can often get away with much smaller samples. So let me, as my last example here, go to SPC acceptance sampling variables. It works the exact same way. I tell it I want to create an OC plan. There'll be 1,000, lot size of 1,000. the AQL is 1, the LTPD is 3, the producers and consumers risks I'll set both to 5. The only difference now, though, is it's going to ask me, do I want to assume a known sigma, or do I want to use a sample estimate? Okay, we could do it either way. I'll just leave it at, I noticed in the notes I just left it at assume known value. If I can assume sigma, I'll get a slightly smaller sample than if I have to use a sample estimate. If I press OK now, though, it will generate for me a variables acceptance plan. And as promised, it's going to be a considerably smaller sample. Now, what it says, and you got to be a little bit careful here, it says take a sample of 55 items out of the 10,000. Measure them. Okay. Take the average of the 55 and the standard deviation of the 55. And then look at this K value, this critical distance. If I'm no closer than this many standard deviations to the nearest spec, you can accept the lot. So basically, I'll compute my mean, I'll compute my standard deviation. If I'm at least 2.10259 standard deviations away from the nearest spec, then I accept the lot. If I'm less than 2.1 standard deviations from the nearest spec, I reject the lot. Right? More work, of course, if you need to measure something. And in some cases, it doesn't make any sense. There's nothing to measure. But if there is something to measure, you can get away with much smaller samples by measuring than just by inspecting and calling things good or bad. Okay. And as I said, the copy of my PowerPoint slides have these two examples in them. In this case, after measuring 55 items, the sample mean is no closer than 2.10259 standard deviation to the nearest spec. We accept the lot. Okay, and as usual, if you need more information, please go to either to www.statgraphics.com or send an email to info@statgraphics.com. Now, let me take a look, if I can, and see whether we have any questions. Let me pull up my little GoToMeeting. And, oh, it's good to see that almost everybody is still with me. I sometimes wonder when I talk for an hour and a half if people might get tired. But, in fact, it looks like almost everyone who started is still with us, so that's good. Oh, and there's quite a number of questions, too. So it looks like we're going to be here for a while, and I'm happy to talk as long as necessary to answer the questions. Actually, before I take questions from the audience, I did have one question sent to me ahead of time. And let me see if I can pull up a slide. Here it is. I think I called it questions. Here it is. This was actually sent ahead of time. This had to do with basically taking samples from a process in order to determine what the failure rate of the process was. And if I understand the problem, what they do is they produce lots and lots of items. Okay, imagine a bunch of items coming off some production line. They want to know what sample size is needed to demonstrate that the failure rate is no greater than 1%. Okay. Now, thinking about this after I read the email, I believe this is very similar to actually what we did for example number 1. When I ask, how do we estimate what proportion of people might vote for Mitt Romney versus Barack Obama? It's a binomial sort of problem. You have two choices. In this case, you look at items and they either fail or they don't fail. What you want to do is take enough samples to demonstrate that the failure rate is no greater than 1%. Now, the way I would set this up is I'd basically set up two hypotheses. I'd set up a null hypothesis based upon P. P would be the proportion of items that fail. And I would say, okay, let's set up a null hypothesis that the probability of failing is greater or equal to 0.01. As an alternative hypothesis, I'll say that the probability of failing is less than 0.01. Now, one of the things you've got to be a little bit careful of when you set up hypotheses is that what you want to demonstrate needs to go into the alternative. Okay? When you do a statistical test, to reject or not to reject, that is the question. You either don't reject the null or you do. So if you're trying to prove something, what you need to prove goes in the alternative. Now, you might be a little bit uncomfortable in that 1%, exactly 1%, is part of the null. But something being exactly equal to anything on a continuous scale, that has a probability of 0. Basically, this says 1% or bigger, that's my null. Less than 1% is my alternative. And what I'd like to be able to do, assuming that I am producing less than 1%, is take enough samples that I can demonstrate at a reasonable level of confidence that I'm producing less than 1% defectives. Now, again, if you're going to do the power approach, you need to pick an alternative. And in the email, they suggested a reasonable alternative. What they usually produce actually is about 1/10 of 1%. Okay? So the way I would set this up, I'd go back to Statgraphics. And let's clear this back again. I'd go to Tools, Sample Size, 1 sample. Again, what I'm trying to estimate is a binomial proportion. Now, in this case, I think the proportion is likely to be around 1%, 0.01. So that's the null hypothesis. I'd now like to ask, how many samples do I need to take so that I can be 95% certain, let's say, of detecting a difference of, now here I got to be a little clever. The null hypothesis is 0.01. The alternative hypothesis is 0.001. Right? So if I have a null of 0.010 and an alternative of 0.001, that's a difference of 0.009. Right? That's the difference that I want to detect. The difference between the null and the alternative. Okay, and what I want to prove is that I am less than the null. Okay, so I wanted to be able to prove with 95% certainty that I'm less than the null if I'm as low as 0.001, which is a difference of 0.009. I hope I'm doing this right. Let's see what it says. It says I need to take 628 observations. Yeah, and again, it's good to read the Stat Advisor to make sure you did it right. It says this procedure determines the sample size required when estimating the proportion of a normal distribution. 628 observations are required to have a 95% chance of rejecting the hypothesis that theta equals 0.01 when the true theta equals 0.001 using a one-sided test. So the answer to that would be 628 observations is capable of distinguishing between 0.01 and 0.001. So if I take 628 observations, I should be able to demonstrate that my failure rate is less than 1%. Now, people get sometimes disturbed by how large the sample sizes are for these binomial problems, but it's the fact of life. You know, if you're trying to determine whether your defect rate is 1% or 1/10%, you don't do that from 25 items. I mean, you just think about it, right? You're trying to prove that you have less than 1% defects. You're going to have to take a lot of items. In this case, about 628 items, it says. Some people have unrealistic expectations. Not the person that sent this email. I'm sure he knew what the sample size needed to be. But other people do have sometimes unrealistic expectations. Okay, well that question was sent to me beforehand. I now have about, how many is it? About 12 questions. Oh, and actually, question number 12 related to this. Someone said the difference should have been 0.09 or 0.009. Well, when it says difference to detect, what it means is the difference between the null hypothesis and the alternative, the mathematical difference. Right? So you take 0.010 minus 0.001. It's the difference between them. You see, what we're picking here is a particular alternative, 0.001, to use as an alternative. That is the one confusing part I know about how we've set up this dialog box. And what it wants when it says difference to detect, though, is it wants the difference between 0.01, which is your null, and in this case 0.001, which is your alternative. So I think I did it right. I think it's 0.009. I know I had to write that down actually on a piece of paper when you weren't watching to make sure I did that right. Okay. Let me read a couple of the other questions. Here's a question. A batch of 30,000 units is to be inspected by taking a sample of 50 units. In order to estimate some attribute, I need to take a certain number of those 50 units and destroy them. Okay, so we're taking a sample of 50 units from a batch of 30,000. Unfortunately, there are lots of attributes that we want to test, so we can't destroy all 50 of those units to measure a single attribute. What's the minimum size of a subsample I can take and destroy in order to estimate a particular attribute? Okay, well that to me, again, that sounds like an acceptance sampling problem, right? You are going to take a sample. Let me call up the acceptance sampling problem here. You're going to take a sample from a lot. The lot has 30,000. 30,000. Okay? Typically, the way our acceptance sampling plan runs is you need to tell us what's good, what's bad, and what risks you want to tolerate. That's the classic way of doing things. However, you're telling me, if I understand the question right, that I can only take a sample of 50. And in fact, I don't even want to test all the 50. Well, there's another option on the dialog box, on each of these dialog boxes, that says Analyze Existing Plan, which allows me to tell it what I want to test, what plan I want to use. Okay, well, let's suppose we do have 30,000 samples. Okay, let's decide to destroy 25 of them. The question said there were 50 units, but I didn't want to destroy them all. Maybe we can destroy half of them. And let's put in an acceptance number of 0. Now, what I'm telling it now is what plan I'm going to try. Usually it tells you how many samples you need. I'm going to tell it instead now how many I can afford. And I'm going to ask it to tell me what the risks are associated with that sample. Okay, so it's going to plot now the operating characteristic curve for me. If I do an acceptance sampling plan, which basically says test 25, call it acceptable if you don't see any defectives. Well, what it says is if there's 1% defective, you'll accept a lot about 78% of the time. If there's 2% defective, you'll accept it about 60% of the time. Well, let's widen out the scale. Let me right-click, go to Graphics Options, widen out the X-axis scale to maybe 10% defective items and see what we get. Okay, well, I didn't need to scale it quite that way. Let's see. X, I'll go 0 to 10 by 1. How about that? That'd be a little bit nicer. There we go. Yeah, about 78% acceptance if there's 1% defects, about 60% acceptance if there's 2% defects, still about 20% acceptance probability at 6% defectives. I think in this case where you're not going to be able to take as many as you probably would like, you might as well just pick a number like 25, take a look at the acceptance curve, and see if you can live with it. Can you live with a 20% chance of accepting a lot with 6% defective? If you can, then you could test 25. If you can't, you're going to have to test more one way or another. That's why we put that option in there. Because sometimes people can't analyze any more than a certain amount. So if you click on Analyze Existing Plan, you can put in what you can afford and see what the probability of accepting a lot will be. There are similar options, incidentally, on the other sample size procedures, where you can put in the sample size and it'll show you what the power is, rather than figuring out the sample size from the power. Okay, hope that's helpful. Question number 2. I would like to have more explanation on point 3 of slide 2. Okay. Well, let's go back here to, oh, no, that wasn't the one. Let me go back here to my sample size determination to slide number 2. Okay. Oh, yes, these were the general comments I had made about sample size. Oh, it was 0.3. Oh, yeah. The information gained by each additional data value decreases as the sample size increases. If you look at the width of a confidence interval for example, for a proportion. We've done a lot of sampling in binomial situations today. You'll notice that the confidence interval goes plus and minus typically 2 times the square root of p, 1 minus p, divided by n. The important thing about that is that the width of the confidence interval is proportional to 1 divided by the square root of n. So let's suppose I started with 1 observation and doubled it, took 2 observations. Well, instead of being plus and minus 1, the confidence interval is plus and minus 1 over the square root of 2. Okay. And then I take another observation, it goes down to 1 over the square root of 3, then 1 over the square root of 4, then 1 over the square root of 5. Because of that square root in the denominator, it means that when I take that second observation, the confidence interval decreases a lot. When I take a third observation, it decreases a lot, but not quite as much as it did before. When I take the fourth observation, the confidence interval tightens, but not quite as much as when I took the third observation. If you look at the margin of error and you start increasing the sample size, as you go from samples of 1 to 2 to 3 to 4 to 5, you see a very quick reduction in the width of the confidence intervals. But as the sample size gets larger, the addition of 1 more data point has less and less effect on the width of the confidence interval. Okay. In general, if you want to cut your confidence interval in half, you need to take 4 times as much data. Okay, so that as you take additional observations, the information that you get and the width of the confidence interval basically is proportional to the information. The information goes down with every additional data point, but not as quickly as the sample size gets large. So although it can be very important to change from 4 observations to 8, you don't gain as much when you go from 8 to 12 as when you went from 4 to 8. Okay, third question. What if the sample is less than 30? Some samples are less than 30. I generated some situations here. I think I had some examples, in fact, right, when there was less than 30. Now, the only reason that 30 is any sort of a magic number is that that is large enough so that if you are estimating a mean, okay, as I did, for example, here, when I had a new process and an old process. If my samples are 30 or greater, we're fairly comfortable that the what's called the central limit theorem will take hold and make these means act as if they follow a normal distribution. Okay. If you have very small samples and the individual measurements don't come from a normal distribution, then the means may not follow a normal distribution the way things like a t-test and so forth typically assume that they will. So if you have less than 30 observations, the normality of your observations may become a problem. I think that's where the number 30 came from. 30 is sufficient for almost any process, regardless of how skewed it might be, for the means to act like they follow a normal distribution. That might be a little bit off, but it's still pretty good. What you could see, for example, in this case, it said I should take 13 observations from sample 1 and 13 observations from sample 2. That was the solution to my second problem. And if you read the Stat Advisor, it does say this procedure determines the sample size required when comparing the means of two normal distributions. Okay. If they're not normal, then things are not going to be quite right. The t-test's not quite right. But the central limit theorem takes hold pretty quickly. I mean, 30 is a rule of thumb that people like to use that almost anything type of distribution will generate means that follow a normal distribution if you take 30. But I would be more concerned about it, the assumption of normality, I guess, if I did have less than 30 observations. Other than that, I don't know any real magic about the number 30. Okay. Question number 4. Confidence intervals for proportions can be calculated using a dozen different methods, each of which give intervals of different lengths. For example, there's an exact method, a score method, a normal approximation method, a z-table, a reasonable method. Which method does Statgraphics use for binomial sample size determination, and why do you choose that method? Okay. Let me see. I'm not sure I know the answer to that offhand. However, there is documentation available for each one of the procedures in Statgraphics, and we have tried to document as much as possible the methods that we use. So let me go here to the Help menu and pick up procedure documentation. There is a PDF file that you can get to from the Statgraphics Help menu that describes what methods are being used to estimate and to run any particular procedure. And I see, oh, I'm lucky, I have both the English PDF files and the French PDF files. I'd actually installed both the English and French system here. Since I read English much better than French, I'm going to pick the English version of sample size determination, one sample. Okay, this should bring up a PDF file. I have to give it a moment here. Okay, it's going to bring me up a PDF file. And I do believe there's some equations showing how sample sizes are determined in this particular file. Okay. Yes, there's quite a number of calculations here. And let's see if I can scroll down to binomial. Okay. I'm going to have to zoom this a little bit, or you're not going to see anything, and neither will I. Let's see, zoom to, let's say, 200%. Well, that might be a little much. Or let's widen it out and see what we can see. Actually, that might be good if I widen this out a little bit. There we go. Okay. What are we interested in now? The question had to do with estimating binomial proportions. Okay. Or figuring out sample sizes to estimate the binomial proportions. The way we solve the problem here is if you're using the margin of error method to estimate the binomial proportion, and you tell us you want to have a margin of error no more than W. When you think the proportion is this value theta, we'll find the smallest n such that something involving an F distribution is less than W, and that's less than W, where V1 and V2 equals these two numbers. I believe that is an exact method in the case of the binomial proportion. It involves using something involving the F distribution. Often people use the normal distribution. That's an approximate method. I believe that that's an exact method in the case of the binomial. In the case of the binomial proportion, if we're basing it on the power, it says find the smallest n using exact probabilities for the binomial distribution. Yeah, now I remember. In the case of the hypothesis test regarding the binomial, we compute the power exactly. We actually take the binomial distribution and in any particular alternative compute binomial probabilities so we get the exact power. And we search numerically for the smallest n that gives us the exact result. Wherever possible in our sample sizes, we're going to be, since we have a large computer behind us, not using simple approximations like you would see in a textbook where you have an equation for n, but instead using the exact probabilities and letting the computer, start with a particular n of, let's say, 2, and then increase it to 3, and then increase it to 4, and find the smallest n so that the exact probability is what you need. No reason to use an approximation when you have a powerful computer that can do the exact result. So anyway, the information about how we do it is all in those PDF files. Does CPM stand for capability of the process for a machine? Well, now that's an interesting question. CPM, again, I'm going to have to go to the procedure documentation. I think that CPM actually stands for capability of the process modified, but I'm not sure. I can show you what it is, though. Let me go to process capability, or maybe it's just called capability analysis. Here it is, variable data, and see if I can quickly show you the equation for CPM. I know what CPM does. CPM is a modification of the two-sided CP index that takes into account how far off-center your process is. If we look at the definition of some capability indices, let's see if I can find them here. I know they're in here someplace. I just got to find them. Excuse me for this. Oh, here. Now I've gotten close. Oh, here we go. CP, the normal CP statistic. It's a two-sided capability index. It's the distance between the upper spec and the lower spec divided by a multiple of sigma, usually 6 sigma. Upper spec minus lower spec over 6 sigma. One of the criticisms that people have had for years about the capability index called CP is that nowhere in that process, in that equation, do you see the process mean. A process can be way out of spec, way off center, and still have a good CP. Okay. What the caller was probably thinking about was CM. CM is machine capability. That's actually upper spec minus lower spec over 8 sigma. What CPM is, I think it stands for CP modified. And that's what the documentation says. It says it's a modified version of CP, measuring variation around the target rather than the estimated process mean. So you actually take your CP, divide by the square root of 1 plus something involving the difference between your mean and your target value. The thing about that is that it decreases the value of CP if you're way off center. So if you're significantly off center, the CPM statistic may be considerably less than CP. It's still a two-sided capability index, but it incorporates a measure of how far off center you are. The reason we do sample size for CP, CPK, and CPM is for each of those there's a known way of getting the confidence interval. We could probably also do it for that machine capability index CM. I may have to add that to the list for the next version. But no, it's this modified CP designed to measure whether you're off center or not. It's being analyzed there. Okay. Oh, here's a question. Why not include PPK sample size calculations since PPK is widely used? The only difference typically between CPK and PPK would be the estimate of sigma, whether you use a long-term or a short-term sigma. Okay, and you can see in the documentation, for example, let's go down to CPK. It puts a sigma hat in the denominator. And if you're talking about a CPK, you're using what's typically called what Statgraphics calls a short-term sigma, which if it's coming from an X bar chart is typically a within-group sigma, versus PPK, which is long-term. Yeah, I don't know that there's really a difference in the confidence intervals there. So I actually believe that the results for CPK and PPK would probably be the same. That's an interesting question. I hadn't thought about that. I knew I was going to get some good questions this time around. Someplace we do have here in a confidence interval for CPK. Let's see if I can find it and look at the equation. I think it's in here. It may not be in here. I actually think that sample size selection would apply. Oh, there it is. There's confidence interval for CPM, confidence interval for CPK, and okay, so the confidence interval for CPK is the estimate times something involving a normal distribution and something else involving a normal distribution. Yeah, that's probably, you're right, specific to CPK. I'll have to do some research on that. Okay, I'll do some research and see if I can post a note on the website someplace about what would happen for PPK. I'm not sure exactly where those confidence intervals are derived, so my thought is it might also be applicable to PPK, but I want to double check that before I say that for sure. Okay. Oh, and then someone also questioned whether or not I was actually calculating PPK in my example and not CPK. What I was actually doing in the example is I was looking at this confidence interval right here, okay, and solving for n so that this number here was no more than 1.1. Remember, we wanted to get within plus and minus 10%. Okay, well, we'll get within plus and minus 10% if what's within the brackets here is 1.1. And what you do, what the computer does, is it finds a sufficient n so that what's in the brackets here is 1.1. Okay. Let me do a little bit more research on exactly where that equation comes from, and I'll make a note about whether or not that's appropriate for PPK, CPK, or both. Oh, and now I have a note from our dealer in France. He says, what about sequential sampling? You didn't cover sequential sampling. You're right. I guess I forgot. That was just added to the latest version of Statgraphics, sequential sampling. Well, I don't have time to do that now. I've gone way past my hour and a half. All right, I'll have to talk about sequential sampling in an upcoming webinar. Yes, I could have put that in here, but I just actually didn't think of it. Sequential sampling is actually where you don't come up with a sample size up front, like take 130 observations, go ahead, collect all 130, and then make a decision. In a sequential sampling, you can basically start out, take your first observation, your second, and your third, and as you're collecting the data, start computing the statistics. And if things are really good or really bad, you might be able to stop the test very quickly without having to collect a very large sample size. So yes, to Christian Charles back there in France, I will have to talk about that in a future webinar. Okay. Someone says, I have version 15 of Centurion. My sample size menu doesn't look like yours. You're right. For example, tolerance limits is not listed, and the samples are in other places. How can I get my menus to look like yours? Well, there's only one way to get your menus to look like mine, and that's to get version 16. The first two sample size choices, one sample and two samples, are in version 15, together with the acceptance sampling. Statistical tolerance limits, capability indices, control charts, screening designs, these are all new with respect to version 16. So the only way you can get those four choices is to get version 16. It was one of the improvements we made when we did version 16. Okay, question number 10. Variable sampling plans work only if the population is normally distributed. Does Statgraphics make that assumption, and if not, why not? It certainly does. It certainly is based on how many standard deviations. The mean is away from the spec, and that's only going to be relevant if, in fact, you do have a normal distribution. So the question is absolutely right. The acceptance sampling plans based on variables assumes that either the data are normally distributed or that you can find a transformation to make them normal. So, for example, it would work for log normal data if you first took the log of the data and the log of the specs. Then you could use it. But yeah, absolutely, we're doing nothing special here. It's traditional acceptance sampling based on variables. Incidentally, if you're interested in a reference that does a good job on acceptance sampling, Doug Montgomery has a book on statistical quality control, and his section on acceptance sampling will give you the details on many details on our acceptance sampling plans. We followed Doug Montgomery's development quite closely when we put our acceptance sampling in. See if I can get you the reference for that. There's actually a PDF file here called References, and let me see if I can find Doug Montgomery's book. It's going to be down here under Statistical Process Control someplace, I'm sure. Montgomery, there it is. We're going to, again, have to make this a little bit bigger. Come on, Adobe, you can do it. There we go. Here it is, right down here. Doug Montgomery, Introduction to Statistical Process Control. The last edition I saw was the 6th edition, 2008, John Wiley and Sons, although they may have another edition by now. Anyway, very good section on acceptance sampling. And we actually followed that development very closely for both the acceptance, the attributes plans and the variables plans. So if you're interested in more information, that's a good place to go. Okay, question 11. How could I determine the sample size when having 2 test factors and different parameters to measure for each factor, such that the size is enough for each parameter? I gather what we're asking here is that what you're saying here is that you're going to take samples, okay, and from each sample you're going to measure 2 different things. You measure, you know, viscosity and purity, or weight and height. How do you determine a single sample size when you have more than one variable to measure? I assume you do it separately for each response and take the worst case scenario. I really don't know any other way to do it, although somebody has probably come up with some fancy way that I'm not aware of. I mean, the obvious way to do it is if you have more than one response is to figure out the sample size for each variable separately and take the worst case. You know, you'll just have more information than you need on the second factor, but at least you'll have what you need for the first factor. If anybody knows something more clever, let me know. Okay. Oh, someone says that this was a good nuts and bolts approach to determining statistics governing sampling. Can you recommend an article that describes the difference between binomial and attribute sampling in single syllable management terms? That's an interesting question. Again, I'm probably going to go back to Doug Montgomery's book. You know, there are books that are written for statisticians, and there are books that are written for practitioners. I think Doug Montgomery does a good job in giving you enough mathematics that you understand where things are coming from, but setting it in enough of a practical perspective. I don't know of one necessarily written solely for managers that don't have a technical mathematical background, but I think Doug probably comes as close to anything that I'm aware of in terms of doing a practical introduction to sample size selection, particularly on the acceptance sampling. And he also covers the control charts and the capability indices and so forth. When dealing with custom parts, this is another question, job to job, in discrete lot sizes of 80, do you use the margin of error method or the power method to determine a sample size for a variable measurement for measuring variables. So you're doing custom parts, discrete lot sizes of 80. Well, if your lot is as small as 80, then the assumptions that we've used in some of these procedures, some of the binomial sampling, that you're sampling a relatively small fraction of all the items is not going to hold. If you're worried about identifying how many defects you have in a discrete lot like a lot of 80, you're probably going to have to worry about something more like a hypergeometric distribution rather than a binomial distribution. Certainly the confidence intervals are going to need to be corrected for the discrete nature of the lot. I'm going to have to put that one on hold too and do a little thinking about it. You know, I don't know that we have much, to be honest, that has to do with very small lot sizes. But I'll put that down as a question to research. Okay. Certainly the acceptance sampling will go down to those lot sizes. Let me see. When I go down to, I'm just trying to see here under acceptance sampling, for example, for attributes. I think I could probably go down as low as 80. Well, let's see what happens. Let's see what it would say if I want to distinguish between 1% and 3% with a sample for 80 observations. I don't know what it's going to do on such a small lot, whether it's going to be able to do anything. Well, we'll find out. Yeah, it says sample all 80. That's sort of what I figured it was going to say. I'll do a little bit more research on small lots and whether there are anything that we can do that or potentially add to the system to help you out with the very small lots. Good question. I don't have a real good answer for you, though. Okay, more from the person who asked question number 1. Okay. Oh, they're giving me some information. This was the case where we had a batch of 30,000 units. They said the AQL was 4%. There was an acceptance number. Acceptance equals 4. Rejection equals 8. A batch of 30,000 units, they can take 50 for analysis, but they can't destroy them all. Okay. Again, I think I'm going to have to follow up via email with that particular question. See if we can find out a little bit more of exactly what they need to do. Okay. That's all the questions I have. Yeah, if you didn't get the answer that you were hoping for from me, please make sure you send me an email directly. Send an email to Neil, N-E-I-L, @statgraphics.com. Give me a little bit more information if you can. Give me a little bit of time to mull over it, and I'll see what I can do. I'm going to post some information about CPK versus PPK. I'll try to put a link on our webinars page. Okay, when I get delve into that a little more deeply, I'll put together a few notes go to the webinars page for this particular webinar, and I'll try to post some notes about CPK versus PPK with respect to sample size. Other than that, half of you are still here, so that's makes me feel good. I did talk for quite a while. And I thank you all for listening. Now, the next webinar will be sometime probably near the beginning of February. If you have some topics you'd like to hear covered, please, again, neil@statgraphics.com. Give me an idea of what you'd like to see covered, including the sequential sampling, which I'm going to have to put in at some point. Other than that, have a good day. Thanks a lot.